In a collision involving a car equipped with airbags, the impact initiates a chemical reaction. Automobile airbags work when a sample of sodium azide detonates, producing nitrogen gas. This gas fills the bag. Using our understanding of the gas laws, we can calculate the quantity of sodium azide required to produce the appropriate amount of nitrogen gas.
A lot of people know people that have been saved in a bad car wreck because of airbags, and I have family members that have been saved by this too. And airbags are a direct result of scientists' understanding of the gas laws. In the airbag is usually a sodium azide. That's that NaN3 thing down there. And it's a solid, but it can be disturbed, and it ends up making sodium metal, but more importantly here, nitrogen gas, N2. And the gas is what expands. It creates like a cushion, so that you and your body don't get hurt too bad, which is incredible. So gas laws are definitely important, and they've saved a lot of people over time.
According to the kinetic molecular theory, the molecules of a solid are locked in place, though they have motion. Molecules of a liquid are closely associated with each other, but move relative to one another. Molecules of a gas move independently and occupy a much larger volume than those of a corresponding liquid or solid.
So as a reminder as to how chemists see the differences between solid, liquids, and gases, I'll remind you about what's called the kinetic molecular theory, the KMT. And that basically states that solid molecules are locked in place and they don't move around very much. At 0 Kelvin, even that movement would stop, but there's always some movement in solid. Liquids, on the other hand, there's a connection between them, but it's a lot less rigid than the solid. So liquids do stay together, but you can pour them and they'll take up the volume of the space that it occupies. Gases, on the other hand, there's no interactions between them at all. All right, they kind of move around on their own. They collide into each other, but it's no big deal. So you can see the differences here. Now, again, it's important to remember that solids, liquids, and gases, it's all the same. So if we're talking about water here, ice would be the liquid version of water at a low temperature, so that's why it's solid. Liquid water would be, of course, drinking water, and then gas would be steam. So those blue molecules in this model would represent H2O. It's just the interactions between the H2Os, which are different, that makes solids different than liquids, which are different than gases. We're going to look at gases in this chapter a lot. In the next chapter or so, actually a couple chapters, I guess, we will look at solids and liquids in more detail. Now, in addition to solids, liquids, and gases, there is a fourth state of matter called plasma. And plasma in the universe is the most common phase of matter. We'll look at plasma in chapter 20, but it's not super common on the Earth. Well, again, we'll talk about that more later, but I just wanted to tease you. Check out the little pictures of the sheep up there. Those are great representations of gases, liquids, and solids. So in gases, the sheep are just all over the place, no control. Liquids, on the other hand, you can see they're all kind of trying to get through that one little area right there. That would be liquid flowing through a container. And on the other hand, solids there are hanging out very tightly together. All right, I have a strange sense of humor.